Welcome to a lesson with Dr. Pal. Let's take a look at how we can solve a system of equations using cofactors. So this is an extension of the last video that we had. We're going to be working with the same matrix here in cofactors in part of it. Let's take a look at the system of equations we want to be looking at. Um, the coefficient matrix looks like the same one we were investigating in that video. Um, and here's what we're trying to equal on this side is 1, negative 1, 2. All right. And so that's what we'd like to solve. Now, of course, if we thought of this as we take this matrix and we find its inverse, so calling this matrix, if this matrix right here is A, then if we multiply it by its inverse on both sides, that should solve it because the identity times xyz would just be xyz is equal to that. So we would get the solution if this matrix has an inverse, which it does. We saw it in the last video. Because the determinant is non-zero, we can take an inverse here. So in order to find xyz, we just may need to make this computation. Notice to find the x coordinate, we just run this row times that column right there. So row times column. And then, of course, we need to divide by -4 in order to get our x value. Our y value, we do this row and that column, okay, and we divide by -4, we'll end up getting that, and similarly for z. Well, let's think about this, though, and what's happening in terms of cofactors. This row right here, so I'm kind of keeping this off the side, this -1/4, but let's just think about this row. What does this row mean? This row is the cofactors associated with the first column of this matrix A right here. So remember how we did that? So take a look at this. So we looked at this first column here, and going down these entries with a plus, minus, plus, we found the cofactors associated with this guy. That was that. This guy is that. And for this guy is that. Okay. And we're writing it as a row. Now, remember that this actually, that every time I do this for each one of these, so that guy as well as the middle guy here, is a function. It's a linear transformation from R3 to R. It outputs the determinant of the matrix, where the column that we're focusing on the cofactors coming from is replaced by a vector. Okay, so that's the input vector in R3, and it outputs the determinant if that column was replaced by something. Now, notice, let's think about that interpretation in this matrix multiplication that we have in order to compute what xyz is, because this row right here, that's one of those functions. Like this is one of those functions, when this is our input vector. So what does that mean? That means, so since this came from the first, these are the cofactors associated with the first column, that means replace the first column with this input right here and take that determinant. You'll notice that this determinant is the same as this matrix product right here. They're this one and the same. That was an interpretation of what this dot product means. And so you can compute it either way, and you get 6. Divide by -4, and you'd end up getting -3/2. So here, likewise, to find the y coordinate, we compute this determinant right here, where we've replaced the middle column of our original matrix with the output here, 1, -1, 2. Okay. And that'll give us this value, which then we divide by -4 to get the y value. So think x, we're replacing like the first column, y replacing the second column, z replacing the third column, and repeating, doing the exact same thing. And we can solve the system of equations then by, even if we didn't know what the inverse matrix was. What if we don't know what the inverse matrix is? I mean, like using this, we need to know we compute like rows of the inverse matrix in order to make these matrix computations here. But what if we didn't even have that? We could just take a determinant that's an equal description of what this row is doing as a function. It's taking a determinant of the original matrix with something uh, plugged in for the corresponding column. Like this input here is the input into this function, and what it outputs is the determinant with where this is replacing like the first column. This is the determinant where this is replacing like the second column, determinant where this is replacing the third column in that case. So we don't even need to know what these rows are in order to do this. We don't even have to compute the inverse matrix in order to solve the system. We can just look at these determinants. It's kind of a nice idea. This setup, this is called Cramer's rule. Just looking at determinants to solve the system. Okay, and this works for an independent system, one that where there's only one unique solution, and where the matrix has an inverse, it's invertible, kernel is 0. Okay, so let's take a look at another quick example, 2x2 example. This is just a really simple system of equations, but note here's the coefficient matrix. We can compute what the x value is by computing this determinant, dividing by the determinant of the whole of this coefficient matrix. Notice like we were doing times 1 over -4. Here we do times 1 over 5 because 5 is the determinant of this matrix right here. So 2 minus a -3, that would be 5. So we're going to have divided by 5 each time. Then we take right here, we take the determinant of this matrix where we're replacing the first column with these this output here 4, 1, and computing the determinant 8 minus 3, that's 5. 5 over 5 is 1. All right. Then we do this similar thing for y, where we take this matrix, replace this column with the output 4, 1, find this determinant 1 minus a -4, so that'd be 5 over 5 is 1 again. You can check it. Sure enough, 1 plus 3 is 4, minus 1 plus 2 is 1. All right, so this is just a little example of using Cramer's rule and describing why and how it works. Thanks for watching.